In this section, we are going to introduce a really useful technique for integrating functions that we haven't been able to integrate yet. And it is called the substitution method. And I want to start with this example. It's kind of a really clear example. And the reason why is what you see here is I have like cosine of x cubed. So I have a function inside. So this is a composition of two functions. Okay? It's like I have cosine of, and then inside here is x cubed. So there's an inside function and an outside function. The cosine is the outside function. Inside that is x cubed. But what I notice is, in addition to that, I got 3x squared. And 3x squared is the derivative of x cubed. And because I have that, I can take the antiderivative, okay? The antiderivative of cosine here would just be sine. And then I have an x cubed here. And then I'll just do a plus c. And this 3x squared is just what I would have gotten when I used the chain rule. Okay, so in other words, if I take the derivative of this, sine of x cubed, so if I'm going to take the derivative of that, I'm going to take the derivative of the outside function, which is cosine, evaluate it at the inside function, but then I have to multiply that by the derivative of the inside function. Oops. 3x squared, like that. Okay, and so basically this here is what I got here. So since this was in my integral, then I can go backwards directly to sine of x cubed. Okay, so what I'm really doing is I'm doing the chain rule in reverse here, but I was fortunate enough to have the derivative of the outside function, or the derivative of the inside function, just hanging around. So by hanging around, I mean it's a constant multiple to the function. Okay? Because since it's a multiple to the function, then I can reverse it. Okay? So now, consider this. Now consider the following integral. Let's say I had cosine of x cubed, and then I had x squared here, dx. Okay? I no longer have the derivative of the inside function hanging around on the outside, right? But the difference is I lack a constant multiple. If I had a constant multiple of 3, then I could do it. Well, if constant multiples are never a problem because you can pull constants out of the integral. Okay, so I could do like 3 over 3, which is like 1, right? And then I could pull the 1/3 out. And then I would have cosine of x cubed, and then I would have the derivative here on the outside, and so then I could reverse and I could do sine of x cubed plus c. Okay, so really I can use this rule if the function on the outside is even if it's not the derivative, if it's proportional to the derivative, or if it's equal to a constant times the derivative, or I should say if it's lacking only a constant multiple and then it would be the derivative, you can still reverse the chain rule here, just like I showed you, by bringing in the constant that you need and then bringing the reciprocal on the outside, and then you're good to go. Okay? And so, so that's really nice. Okay. So now let me actually write out and kind of show you with some notation here what this is doing, and then let me apply a different method here to do this. Okay, and this is going to be kind of an official substitution method. What I want to do here is just recall that the chain rule is when you have the composition of two functions, right? I got g of x inside of f of x here. And so I take the derivative of f of x, evaluate it at g of x, and then I multiply that by the derivative of g of x. Okay? And so what I just showed you here is if you have some function and you have another function inside it, if you have this constant if you have the derivative of the inside function hanging out on the outside, or even if it's different by only a constant multiple, then what you can do is you can reverse the chain rule, and you would get this. Okay, so if you have an outside function with an inside function, okay, if you have an inside function inside an outside function, and you have the derivative of the inside function hanging on the outside, you can reverse the chain rule. And even if this isn't quite the derivative of the inside function, if it differs by only a constant multiple, then you could reverse it, and you could even well, let me just leave it like that, okay? And so you're reversing the chain rule. Now let me show you a way of looking at this, because this is basically kind of what the substitution method is. But let's say I have this integral, and I have the derivative hanging out on the outside with respect to x. Here's the idea. What I'm going to do is I'm going to let u equal the inside function. Let u be equal to the g of x. Okay? And so sometimes they call this a u substitution, or a u sub. Okay? So what I can do here is I can take the derivative of u with respect to x, and I'm going to get g prime of x. Now here's kind of the interesting thing is treating these like they're two separate quantities. I can say that du is equal to g prime of x dx. So I'm bringing the dx over to the other side, like this. Now notice what I have over here is what I have right here. Okay, so this is equal to du, and the g of x inside the f is equal to u. And so what I can do is I can rewrite this as f of u, replacing the gx with u, but now I can replace the g prime of x, d of x, with du. And so what you have here is just a simple antiderivative. If you know the antiderivative of that, f of u plus c, which now I can put the g of x back in, plus c. And of course this is where f prime, capital F prime of u would equal, f of u. Okay, so in other words, this is the antiderivative of that. And so this is kind of a method then. If you have the composition, an inside function, inside and outside function, and you have its derivative hanging on the outside, you bring these two together, right? And then you let u equal the g of x. You take the derivative of u, then you bring, and this is the weird part, because this is just notation for the derivative, but this works. You can bring the dx over here, and then you get this portion. And what that means is I can substitute this portion in for the du, and then substitute the u in for the gx, and then I'm simplifying my integral. And this makes it a real nice method that allows you, just makes it a lot easier to go through and think about. It makes it a very systematic method. So let me show you with the one that we just did. So let's say I have the cosine of x cubed, and then I had 3x squared dx. So what I would do is I'm going to let my u equal the inside function, then du dx would equal 3x squared, and now I'm going to bring the dx over, split that up, and I know that's a little strange, but you can do it for this and use this technique. So you got this, and this is right here, okay? So I can rewrite this integral as cosine, and x cubed is equal to u, so this is like the cosine of u, and then all of this, 3x squared dx, is equal to du. And so now I just have a simple integral, and now the antiderivative for that would just be sine of u plus c, and then to finish off I can put the x cubed back in for u. And I get my final antiderivative, and you can see that that's what we got here, right, when we did this. Okay, so this is a real nice, there you go, right there. So this is a real nice method, okay, of doing this. Oh, and you know what? When I did this and I came over here, I made a mistake. This should have been 1/3 here, shouldn't it? Hopefully you caught that. That 1/3 on the outside. I just caught it now. See, even your teacher makes mistakes. So now let me show you another little trick that's nice with this. So let's say I have that one where it differs by a constant multiple. So let's say I just have x squared here, dx. Okay. Now I notice there's an inside function. I almost have the derivative of the inside function on the outside, but it differs by a constant multiple. So this method will still work, and it gives you a real nice way of doing the problem. So and this is the way. So you're going to let u be the inside function, x cubed. Now I'll take du dx is equal to 3x squared. Okay, and then this du is equal to like 3x squared dx. Okay, now I don't have a perfect substitution here. Okay, but if you're dealing with just a constant, then what I could do here is I can take the 3 and bring the 3 to the other side. 1/3 du is equal to x squared dx. As long as this is just a constant multiple that you can pull out, you're good to go. Now I got the substitution, x squared dx, x squared dx. What do I substitute here? Not just du like I did here, but 1/3 du. Okay, so this would be the integral of cosine, put in u for x cubed, and then for x squared dx, put in 1/3 du, like that. Then you could pull out the 1/3 the integral of cosine of u du, and then I get 1/3 sine of u plus c, and then finally 1/3 sine of placing the u back in, which is x cubed plus c. And there you go. It's such a nice method. Okay? This works very, very well. I love this method. It's like my favorite. So let me do one more, and then in the next video we'll do a bunch of more examples of this. So what I'm going to do is I'm going to do this one. Let's say I have x over the square root of x squared plus 1 dx. Okay, so now this one's a little trickier here, but let me write it like this. What I notice here is if I had something like this, that this x here, it'd be like x dx. The x here is almost the, if I let x squared plus 1 be my inside function here, the x is almost the derivative of x squared plus 1. So the derivative of x squared plus 1 is 2x, right? So this differs by only a constant. So I can use this as my u. It'd be x squared plus 1. Then my du dx would be 2x, right? And then my du would equal 2x dx. Now this substitution, I need just the x. I don't want the 2, so I move the 2 to the other side. 1/2 du is equal to x dx. And so now I can substitute 1/2 du for this, and then I can substitute u for that, and this becomes 1 over the square root of u, and then I have the 1/2 du, right, like that, and that's just a constant multiple. So I can pull out the 1/2, and then I can write this as a negative fractional exponent, u to the negative 1/2 du. So it would look like that. And then I can use the power rule on that. So notice how it just simplifies this complicated thing to something very simple, okay, with a variable of u. And so then I have the 1/2, and then using the power rule, this would be u to the 1/2 over 1/2, right? And it would be all that plus c. And then I can invert and multiply this 1/2, and that actually cancels this one out, and I'm left with just the square root of u plus c. And then I can put the u back in, and I get the square root of x squared plus 1, and all of that plus c. And that would be my final antiderivative or integral of this. So just like that. This is a nice method where you don't have to think so much about, oh, how do I do this derivative backwards and bring in what I need, and am I doing it all right? It's a method that works kind of on its own. Find the inside function, find the substitutions, put it in, integrate. It's beautiful. I love this. I love this method, okay? And I think you will like it too. In the next video, we'll do a bunch of examples so you can see it at work. And then what I'm going to do in the final video, I think that there will probably be maybe 3 videos. We should be able to cover it in that many. But what I'm going to do is I'm going to show you how this substitution method can be used in and of itself, not just to reverse a chain rule, which is kind of what we're doing here, But it can be used in other clever ways to do integrals where you don't necessarily have the derivative of the outside function hanging out on the outside. You have something else, but just you can do substitutions. You can make substitutions, and things will reduce down and simplify into things that you can integrate as long as you do your substitutions correctly. And it's really, really cool. So, and it ends up being the harder problems that are at the end of the homework end up being little puzzles that can be very challenging, but also I think they're pretty fun. So I hope you find them fun as well.